Dieter Lang from Ashram in Germany speaking. And some of you know this is interesting because it's 6 a.m. my time in Hawaii and it's 6 p.m. his time in Germany. So this is the first time I've done something with a total 12-hour gap. So, Dieter, your turn.
Okay, thank you, Stan. Hello, everybody. I will start right now before maybe everybody is in. I see 11 participants so far, but let's see how many will join us in the next time. So, well, the first problem. Okay, just an official page, a disclaimer. Whatever I will tell you, you should not use it to take a decision on buying or not buying Osram shares. I have to tell you this formally because it is important that you notice this. Whatever I tell you is not related to Osram business. It's a scientific talk and should not be based for a business decision. Some words on myself. I've studied physics and computer science in Germany at the University of Kaiserslautern. I joined Osram in 1984 in the
Excuse Dieter, please. Anybody that has a phone, please mute it. Thank you. Go ahead, Dieter.
I joined Osram in 1984. This means I'm with Osram since almost 30 years. I started in the Central Lamp Development Department working on Xenon discharge lamps for automotive applications. Then from 94, the next 10 years I worked in the Central Research Department again on HID lamp, ceramic metal halide lamps. And since 10 years I'm working on light and health. Osram is calling this light and quality of life. That's our internal name for this topic. I was in the Central Research Department since that time, first in the Strategic Innovation Management, and since last year in Research and Innovation Group in Corporate Technology. And since that time, since 10 years, I'm working in this field of light and health. At the Dean Institute, I'm convener of a standards committee. Its name is FNL27, Effect of Light on Humans, and I'm a member of the Dean Standards Lighting Standards Advisory Committee. So this should be sufficient to have a first impression about me. The agenda for today, the introduction I've already done. I will talk on basics of biological effects of light on humans. Maybe not everybody is familiar with this topic in detail, so at least some basics will be necessary. Then I will focus on melanopic assessment of light. That's a kind of preview on the current draft for a pre-standard, for a revised version of a pre-standard, which has already been published in 2009, but we have a revised version in preparation, and I will give you a kind of preview on that. And at the end, I will show you some applications of biologically effective light. And if the time runs out, I can also shorten this part 4 a little bit. The first, now basics about biological effects of light. First, some remarks on my understanding of human-centric lighting. You know, since 100 years, we think to know a lot of visual effects of light on humans. This is everything related to seeing, to perception, to colors, but that's not all. We learn more and more about so-called non-visual effects, sometimes also called biological effects. This is a field which is not so well known. We just learn more and more since about 10 years. But it turns out that this is also highly relevant for illumination. And of course, not to ignore the emotional effects, everything related to well-being and comfort, which is also influenced by lighting. is a third field which is often, let's say, kind of ignored in technical lighting design. All these three things together, they have to be in a kind of balance. And for me, from my point of view, human-centric lighting requires a balance of visual, emotional, and biological needs of humans in lighting application. And so when I'm focusing now on non-visual effects and biological effects, this does not mean that these biological effects have a higher importance than the other two aspects. But these other two things, visual effects and emotional effects, they are known since many years, and I will not focus on this in my following presentation. The non-visual effects are mainly based on two different. Let me ask you a question. Can you see my mouse? The mouse moving?
Yes.
Yeah. Okay, fine. Then I can use this instead of a pointer. From the retina, from the human retina to the brain, we have two pathways. The green one shown here is relevant for the visual system. It directly directs signals from the retina to the visual cortex in the brain, and that's where the vision happens. But we have an additional neuronal pathway, which is shown in blue here. And this is the pathway relevant for biological functions. And for biological functions, we have two main different functions. One is the synchronization of the human biology with the external day. And this is performed, for example, through influencing secretion of the hormone melatonin. This is shown here. We have a day-night rhythm in melatonin. During day, melatonin levels are low. During night, melatonin levels are high. And this is influenced by light. If a light is switched on during night, this melatonin level is decreasing. This is called melatonin suppression. That was the process how the effects of light on humans were found first. This was also the way how biological effects can be proven. But this is not the only function. We have a second function, and this is related to daytime activation, to enhancement of cognitive functions, to increase of performance. And this is shown as an example here on the right-hand side. Already 30 seconds after light is switched on, you can see an increased activity in the brain. And this indicates that light is also responsible for enhancing cognitive functions in the brain. This is a relatively new result. Just in 2009 this was proven. And this is of high relevance because this explains that biological effects are much more than melatonin suppression was supposed in the beginning 10 years ago. Now we understand that there are direct effects on the human brain by light, also short-term effects, and these can explain, for example, improved cognitive functions in pupils or improved alertness during daytime by lighting. What has been found 10 years ago was that in addition to the well-known photoreceptors of the visual systems, the cones and the rods, there's a third type of formerly unknown photoreceptor. It's indicated here. Intrinsic photosensitive retinal ganglion cells. Retinal ganglion cells are known since many years, but that some of them have an inherent photosensitivity that was new, and that was just shown in 2001. And since then, we understand much better that it is feasible to address biological effects by a special suitable light. These photoreceptors are only sensitive to blue light, and this is shown here. The spectrum, the full spectrum, is based on a warm white LED, and you see this green function is the visual sensitivity, V lambda curve. This is the sensitivity of the cones. But the retinal ganglion cells, they have their sensitivity only in this blue region. So this green, yellow, and red part of the spectrum is not relevant for biological functions. It's only this blue part. And these functions, these action spectra, how it is called, they are also the base for the assessment of spectral data, of the relevance of spectral data for biological effects. I will come back to this in some of my later view graphs, so it's important already to notice that this blue proportion of the light is relevant for biological effects, while these more green and yellow parts are more important for visual effects. In the assessment of the potential of light to elicit biological functions, you can do the assessment by building the ratio of spectrum weighted by its biological proportion and its visual proportion. So if you have a spectrum like this, LED spectrum, for example, the bluish part is relevant for the biological effects, and if you do the weighting, then a certain amount, a certain quantity of this spectrum is relevant for the biological effects, and this more greenish part is relevant for the visual effects. By building the ratio, the so-called biological action factor can be defined, and this biological action factor corresponds to the potential of spectrum to elicit biological functions. The higher this action factor is, the higher the potential of this spectral composition to elicit biological functions is given. There's a second important characteristics of this retinal ganglion cells. Not only the sensitivity in blue is different to the other photoreceptors, also the location where these photoreceptors are located in the retina is different. And while the visual receptors, the cones, are concentrated here in the foveal region with a very high density and a high resolution, the ganglion cells are more located here in the inferior part, more in the periphery of the retina. And this implies that these retinal ganglion cells can only be stimulated if the lighting also is directed towards these ganglion cells. So the light relevant for vision, for seeing, has to be directed next to the foveal region in order to stimulate these cells relevant for vision. And biological effects have to be stimulated by light reaching these cells in the inferior part of the retina. It has been found, even if there are also ganglion cells in the upper part of the retina, these retinal ganglion cells in the inferior part are more sensitive. And the consequence is that light, which has to be directed towards this inferior part, needs its origin in the upper hemisphere, because through optical laws, light coming from above is directed towards the inferior part of the retina. And it can easily be explained why this has developed in that way. This is, if you look into the nature, it's the blue sky. The blue sky is also in the upper hemisphere, and the light coming from the upper hemisphere, coming from the blue sky, is eliciting biological effects through stimulating the inferior part of the retina where the ganglion cells are located. To transfer this, I have an additional slide here, which is also relevant for daylight, because daylight is only available when the sun is up. During nighttime, of course, we don't have daylight. And to simulate this, we need also the third factor, it's the timing. It's not only, the first one was the spectral composition, the blue proportion. The second one was the distribution where the light comes from, and the third is the timing. Of course, to simulate daylight, we need to have the biologically effective light with higher blue content only during the time when there's also natural daylight available. This means that we can mimic the course of natural daylight by realizing lighting in a way that that the dynamic of the artificial light is oriented on the dynamic of natural daylight. This is shown here. We have warm white lighting, for example, which is shown here. This 500 lux is corresponding to the standard for workplace illumination, and during daytime we can even increase this level maybe to 800 lux. That's just an example. But when during daytime, when we have outdoors natural daylight, we can increase the light levels by adding light with a higher blue content in addition to this warm white light. So in summary, the warm white and the cool white lighting would give a course of light levels indicated here by this green function. You might ask why this green function starts inferior to this. If you add the light, if you add these two light levels, the warm white and the cool white, it should be higher in every case, but yeah, the green is lower. And that is because the warm white lighting has only a very small, a very low blue content, and so the effective contribution to biologically effective light is only about 50% for warm white light. And that's why I call this effective light levels. I will come to this later and will show you how this can also be assessed in a mathematical way. And that explains why I start here with a lower effective light level than just would be the result by adding these two light levels. So from the application concept, when taking into account everything what I have told you so far, we need on one hand side the origin of the light coming from the upper hemisphere. So the lighting has to be distributed in the room. It's kind of mimicking the blue sky. We need visible illuminances at the ceiling and in the upper parts of the walls for daytime illumination. And for nighttime illumination, we should avoid this large area illumination because large area illumination is related to higher biological effects. And if you want to reduce biological effects in the nighttime, you should also avoid large areas, large visible luminance fields. And this is the same now, including also the spectral composition. We have here this higher blue content in the upper part of the ceiling of the wall and on the ceiling for daytime illumination, and for nighttime illumination we again avoid this bluish light in the upper parts of the room.
we concentrate only to task lighting with a more warm white color. So again, in a very brief summary, for daytime, we need light for vision, of course, we need to see, but we also need light for activation and for synchronization. And in the evening and nighttime, we only concentrate on light for vision and do everything to prevent biological stimulation of the biological system. So now in a more mathematical part, I will come to a procedure how to assess the effects of light, or how to assess the potential of light to address the biological system. It is to be seen as a kind of preview on the current draft of a pre-standard, which is ready to publish, but we still hold back publication for a few weeks, and I will tell you in a few minutes why we are holding this back. Here I have an example again of a LED spectrum, and one comment. I'm talking sometimes about biological effects. Sometimes you hear circadian effects. Sometimes you hear non-visual effects, or now melanopic effects. I will talk about melanopic effects. It's basically all the same. The reason why these different terms have been used is just to differ these effects from visual effects. But of course, biological is a more general term. It is not very specific. And also the visual process is of course a biological process. So biological is not clear enough. And circadian is too specific because we have, in addition to the circadian effects, also other acute effects, like for example effects on cognition or on performance. Non-visual is also not specific enough, and melanopic seems to be quite specific because it also indicates that these effects are based on the photopigment melanopsin. These retinal ganglion cells, they contain a special photopigment, giving there this special characteristic of sensitivity in the blue. And this photopigment melanopsin is the reason to call these effects now melanopic effects. The term is also used because it is similar from the wording to photopic or to scotopic, which indicates the sensitivity of the visual photoreceptors for vision during day and during night. So that's a reason to switch to the term melanopic. But in my presentation, it's also kind of mixed up, but it's all the same. So here you see melanopic and here you see biological effects, but it's the same. Okay, this example of a cool white LED again shows that the spectral characteristics can be divided into two parts, into a melanopic part and into a visual part. And when we try to assess light, then we always have to refer to these sensitivity functions. B lambda curve is for photopic vision, and this action spectra for biological effects is for these melanopic effects. There are meanwhile 4 or maybe even 5 different action spectra. I've shown 4 here on this view graph. There are different proposals, and what I'm referring to in my presentation is this blue function here. It has been proposed by Professor Gall in 2003. It is based on the results published by Bert Brainard in 2001. That's this function. And it is also been used in the German pre-standard 5031-100, but it may be subjected to change. So specific numbers which I will show might be changed within the next few months. But now I'm still referring everything I will talk about to this blue function. So an example shown here. You know the V lambda curve. I've already shown it 3 or 4 times in this presentation. That's for daytime vision. We have also a sensitivity function for nighttime vision. That's the dark function here for scotopic vision. And we have a sensitivity function for biological effects. If we want to do a calculation and do an assessment calculating photometric quantities, for example, the lumen output of a light source, then we have by definition the sensitivity at this spectral point at 555 nanometer defined to 683 lumen per watt. This is by definition and can't be changed. If we look at the if we look at the scotopic sensitivity, this is also 683 lumen per watt here at this point at 555 nanometer, which is shown here. But then, just by the ratio of this point to that, it can be calculated that the maximum sensitivity is 1699 lumen per watt. And doing the same for the spectral sensitivity for melanopic effects, this would come out to a maximum sensitivity of 12,418 lumen per watt. And if we would use such a process, such a procedure to calculate the lumen output, the biologically rated lumen output of a light source, we would come to extremely high numbers. That would be completely not understandable to users how the biologically rated light output of a light source could be so much higher than the photopic light output. So we try to prevent such definition, even if this would be the formal correct process to address this or to do a calculation. But we have tried to find a workaround in order to avoid such incredible high numbers for photometric data to assess the melanopic effects of light. Our idea was first to introduce a new unit. This, of course, is not feasible. New units are in principle not allowed. Currently, there's even a discussion to ban the candela as a base photometric unit. So there is no chance to define a new photometric unit, something like biological lumen. This is as a new unit, this is not feasible. But we have thought about how we could find a workaround for this problem, because our goal, of course, is to come to a quantitative assessment of spectral data with respect to its biological effects. And the approach we did was to define standard illuminant D65, which corresponds to natural daylight, as a kind of reference. And our approach was to define that the photometric quantity for vision is the same as the photometric quantity for biological effects for daylight D65. This means that the light source with, for example, 1000 lumen light output with the spectral characteristics of D65 has also a biologically rated light output of 1000 lumen. So for this type of light source, biologically rated light output and visually rated light output is the same. I will show you how this can be done mathematically. The melanopic rated radiometric quantity, that is in watt, for example, that's not yet lumen or illumination level in lux, that's just the energetic assessment. Again, based here as an example on a spectrum of a warm white LED, which is shown here as a orange curve. If this is weighted by the melanopic sensitivity function, the result is this blue function here. And the radiometric quantity is the integral, the sum of this function. So it corresponds to the area underneath that blue function. So the area here is the melanopic rated radiometric quantity. It's sorry for being so mathematical, but otherwise it will not be formally correct, and it can't be easily explained without mathematics. This sounds a little bit more complicated, but it is not really, because it's the same what we've had before. The blue function is again the melanopic assessment. That's the upper curve. That's the same what we had on the slide before. The green part is the visually rated spectrum. And by building the ratio of these two, we come to the melanopic action factor, what we already had, I think, 3 slides before. And now here on this table, you can see some examples. A warm white, this is black body at 2850 Kelvin. This corresponds to an incandescent bulb, shows melanopic action factor of 0.376, while, for example, the standard illuminant D65 corresponding to daylight shows a much higher action factor. This indicates that daylight has a higher potential to elicit biological effects than incandescent bulb. And here are some fluorescent lamp types, 3000, 4000, and 5000 Kelvin. And you can also see that the melanopic action factor is increasing with increasing color temperature. So this is one important factor, this melanopic action factor, which we will need on the next steps. By using this melanopic action factor, that's the same we had before, we can also calculate backwards from photometric data. If, for example, this green function here, if we calculate the photopic weighted radiometric quantity, this is, for example, the power of if we have a power of 1 watt as a photopic weighted light output, then we can calculate that light source having 1 watt photopic weighted light output corresponds to 683 lumen. So from the energetic weighted quantity, we can calculate the light output, for example. And by doing this, we can also calculate backward from photometric data. If I know a light source has, for example, 1000 lumen light output, then I can calculate backward to the melanopic weighted light output by this function. I have some examples later to show this more clearly. But based on all this, we can define a melanopic daylight equivalent. The melanopic daylight equivalent is defined as the ratio of the photo. Oh, how is the? I've forgotten the correct name for this. It's a photopic efficiency of radiation. It's 683 lumen per watt. 683 lumen per watt divided by the melanopic action factor for D65 gives exactly 725.82 lumen per watt. This is the melanopic daylight equivalent. And based on this, we can now do a calculation for each light source to calculate its biologically weighted photometric quantity. Oh, it's really difficult to do this in English, but I hope that we have at least got the basic idea how we do this light assessment. That's what I told you by using this melanopic daylight equivalent, multiplying it with the melanopic rated photometric quantity, we can calculate the melanopic photometric quantity. And I will switch to the next slide, which shows some examples that hopefully makes things clearer. Again, for standard illuminant D65, we have, for example, based on a luminous flux of 1000 lumen, also 1000 lumen as the melanopic luminous flux. But if we go to a classic incandescent bulb, for example 60 watt, with an output of 1000 lumen, then we come to a melanopic luminous flux of only 387 lumen. If we go to a very high color temperature fluorescent lamp with 8000 Kelvin, for example, we will come even to a higher melanopic weighted luminous flux. So for each different type of light source, by knowing the melanopic action factor, we can calculate from the luminous flux or from an illumination level also the melanopic weighted photometric data, just by multiplying the visually weighted photometric data with this factor. For example, red LEDs, which have only a very small, neglectable biological effect, it is only 1% of the photometric output is the melanopic weighted output. For blue LEDs, is of course 10 times as high. And so this will give the opportunity also to calculate the known photometric quantities like luminous flux or illumination levels or even luminance values based on photopic measurements by multiplying with these correction factors. Okay, that was the mathematical part of my presentation. I hope that everybody is still here and did not step out so far. I will come now to some examples for applications. We have done a study in our headquarters some years ago. We changed the lighting from 4000 Kelvin to 8000 Kelvin. 4000 Kelvin is a standard fluorescent tube, 8000 Kelvin is a blue enhanced fluorescent tube. And the idea was to check if higher color temperature lighting can improve cognitive performance and can stabilize the circadian rhythm of office workers. We did this in collaboration with the Institute for Chronobiology at the Ludwig Maximilians University in Munich. This photograph shows that the upper 3 floors were changed to 8,000 Kelvin, while the lower 3 floors still had 3,000 Kelvin. And we had several methods to investigate the effects on humans. We had, for example, sleep logs. The subjects participating in the tests have worn actigraphs showing their activity. They were filling out sleep logs. We had questionnaires. The chronotype was assessed, and this is showing an example from a questionnaire showing lighting acceptance and showing subjective self-assessment, how the light was affecting the people. The inner part shows the results before the light was changed, with still 4,000 Kelvin, and the red line shows after the light was changed, 4 weeks after the light was changed, we did the assessment again. And it shows that all these parameters showed an improvement. The employees had the impression that the light supports their concentration, that it supports their alertness. They liked the new color, also the brightness, and the overall impression was assessed as improved in comparison to what we had before. But this was more a subjective questionnaire, kind of self-assessment. We had also some hard facts, which are shown here on the right-hand side. The phase of entrainment was, that is, the time that corresponds to the time when people get up in the morning, and when they it is a method to assess the sleep, the mid-sleep, the time of mid-sleep that is shown here, mid-sleep on 3 days, MSF. This indicates the chronotype and the stability of the day-night cycle. And it shows that the subjects in the test group with the changed lighting had a more stable day-night rhythm. So this has been published in a paper in 2011. It shows that biologically effective light has the potential to stabilize the circadian rhythm. That is important because it shows that this light is really effective in eliciting biological effects. A second study we have done last year was in 2 schools in Ulm. We changed the lighting from a standard lighting, which is shown here, to biologically optimized lighting, which is shown here. And our hypothesis were that the chronobiologically improved lighting improves the performance of pupils, and our hypothesis was that it can counteract social jet lag, what means that the pupils get more awake and more active early in the morning, because pupils usually are still quite tired in the morning and have problems to get up. This again shows how these 2 classrooms were made. The right-hand side shows biologically optimized lighting. The left-hand side shows the standard lighting, how it is in all the other classrooms. We had the same illumination levels, but we increased, of course, the spectral, we enhanced the spectral composition towards higher blue content. And the results are shown here on the, no, not yet the results. These were the instruments we have used. You can see one classroom here was changed. You see it here in the nighttime photo. This was the classroom which was changed. This classroom here was the reference classroom, and we did several standardized psychological tests. Our study design was that we had two schools, one school here, that's the other school. We did the first test for 6 weeks from November until December last year. Then we switched groups, and the group which was in the biologically optimized group before was afterwards in the reference room, crossover design. And our results, the most important, the most significant results are shown here. We had a clear improvement in visuomotor performance and in attention. We had some more hypotheses and some more effects which were tested. Not each of these effects was really could significantly be proven. I can show you here the green ones turned out to be significant. The D2 error rate was significantly improved. The concentration performance was significantly improved. The number connection test was significantly improved, and also the excitation and agitation of pupils was significantly improved. The other hypothesis could not be proven, but what was interesting was that not in a single case we had a result which was significant against our expectation. So it is quite normal that not every result, every expectation will be fulfilled, but we were happy that we had some really significant positive results and that we did not have a single negative result. The acceptance was also asked by a questionnaire, and a kind of funny result came out. It was more or less 50-50 split. 50% preferred the new light, and another 50% did not like the light, but not because it was bad for them. The pupils did not like that the light wakes them up. They had preferred being able to sleep longer in the school in the morning. So it was kind of positive effect also for those who did not like it, because our goal, of course, was to make them more awake and alert in the morning. We have a follow-up study planned in a school south of Munich. The installation is already done. You can see it here in the upper photograph. That's the biologically optimized lighting. We have a direct illumination from the ceiling, and we have a more indirect illumination to the walls with high color temperature. The lower image shows a photograph of the reference room. And we have a third example. This is a seminar room at the University Munich. You can also see here the bright illumination of the ceiling with high blue content, and direct lighting is more warm white. I see that I'm almost done with time, but not fully done with my slides, so I will speed up a little bit, showing these next examples only in very fast run through. We've done a study in a simulated airplane. It should simulate a long distance flight, but not across time zones. So we did not investigate jet lag. We just investigated the ability to sleep, to recover, and to be active in the morning. And the outcome was that by lighting, we changed like this. The upper shows the standard lighting in an airplane, and the lower shows the new lighting. We changed to a much warmer color temperature in the evening and to a reduced light level slowly going down with the goal to improve melatonin the melatonin excretion, so to reach higher melatonin levels during the night. And in the morning we improved lighting, we increased the light levels, and we increased the blue content with a goal to make people more alert and active in the morning. And so you can see we had a very low color temperature during the night to reduce all possible biological effects to a minimum in the night, and to increase biological effects strongly in the morning. We had a clear improvement in melatonin secretion. It was like we expected. We had an improved stress level, a reduced stress level in the morning. We had a higher activation in the morning, and we also had a higher acceptance and higher comfort and well-being of passengers in this study. So overall, our basic philosophy in lighting is that we need the more blue content in the spectrum to address biological effects. We need a different distribution of light by including walls and ceilings in the lighting concept, and we need the control of lighting through the day by providing the right light at the right time, bluish light with high illumination levels during day and reduced light levels and without blue content during night. So overall, we can reach an improved health, improved well-being, activity, and performance. So the user has clear advantages by biologically optimized lighting. Of course, we can also the environment can benefit by using high efficient, energy efficient products, and we think also the industry can benefit, because if we realize light solutions taking into account the human needs, we will be able to provide higher value products. And so overall, we think that these first studies we have made have shown that a transfer of positive health effects of daylight to artificial lighting indoors is possible. So, and with this, even I've exceeded by 5 minutes, I still hope that everybody is here, and now I'm open for your questions.
Dieter, thank you very much. Can you see the questions in the chat box, Dieter?
Yes, I can see. Well, there are a lot of questions.
Yes. Okay. What I will do is I will state the questions, and then you can answer that, but you can also read them, because some of these are just statements. Okay,
Yes.
Kevin Weilenberg, is it possible to share the full citation to the Vandewella and Deek 2009 paper so I can find the right paper?
Sorry, I did not.
Okay, what I'll do is I'll just email both of you, and you can communicate. In fact, that's going to be good. Okay, Rod Heller,
Yes.
is there a level of blue spectrum illumination that is required for a biological response? You may have covered that because he asked that relatively early.
Um, it is of course always not a sum, but it's a product of blue content and of brightness. So you can either increase illumination level and you can increase the blue spectral part. Of course, it is also a question of energy efficiency. If you increase just the illumination level with a more warm white color, you automatically increase the blue part, because also warm white color has a certain blue content. So doubling, for example, the brightness of a warm white um, um, lighting will have the same effect than changing from 3000 Kelvin to 8000 Kelvin, or maybe from 4000 Kelvin to 8000 Kelvin. This means we use the more blue spectrum because it is closer to daylight, but also because of the higher energy efficiency which can be reached. We don't need these very high illumination levels when we go to more blue spectrum.
Okay, thank you. Now, okay, I know we're getting close to the top of the hour. Dieter, would you be willing to stay like maybe up to 10 more minutes answering
Yes,
questions?
of course, I can stay as long as you like me to stay. That's no problem
Okay,
for me. Um,
okay,
but
so,
some of
so
you might be willing to go to lunch. But for me, it's okay. I can continue as long
Okay,
as you
so
like.
for people that do need to leave at the top of the hour, this will be recorded for committee members only. So if you have to leave now, that's okay. And if you can stay around, that's great. So here's another question. Some people in America have been stating that people should only get a few hours of like 8,000 Kelvin electric lighting in the day, and that sometimes red light is good in the early or mid-afternoon. What do you think?
I think our approach is to provide a light which is similar to natural daylight, and the natural daylight is also blue over all the day. It's just in the few minutes around sunset when light turns more to yellow and red, but during day it's blue all the time. Of course, it's also a question of philosophy. Um, you can, of course, decide to allow, let's say, an hour of relaxation around noon by removing the blue content around noon. But uh, then you have to take into account that maybe not all people want to have their lunch break at the same time. So this should be done on an individual level. If somebody wants to have an hour of relaxation around noon, then you can give this hour of relaxation to him. But if you have a large office space with 20 people, you do not want to synchronize all of them by to the same lunch break time by removing blue light content around noon. It is maybe not necessary to provide this daylight simulation light through 8 hours per day. Um, if the most important goal of the light is to do the synchronization, then it's maybe sufficient to have it for 3 or 4 hours in the morning. This would be sufficient to do good synchronization of day-night cycle. But if you want to have this light in addition to maintain alertness, to maintain productivity and activity during the day, then I would recommend to have this higher blue content like a natural daylight
throughout all the day.
Thank you. And part of that, Dieter, is that there's been some people saying that actually red light can actually be more useful to blue light in the late afternoon for a bump. And I was just wondering your thoughts on that.
I have never heard that red light can have an active effect. Red light can have the same effect as switching light off, because red light does not have a blue content, and red light cannot address these retinal ganglion cells. But it's the same as switching off the light, because if the light is out, if it's dark, you also don't have biological effect. Biological effects can only be stimulated by blue light. So when going to red light, this means you have still sufficient light to see. So red light or yellow light can support the visual process, but it does not affect the retinal ganglion cells. So for me, red light or yellow light is only a measure to enable the visual process, but to prevent to elicit biological effect. I have never heard that red light has an effect to increase or to strengthen any biological effect. I don't know any study indicating this.
Thank you. And just want to let you know there were a whole bunch of questions from Milena Simonova. And I'm just going to have both of you connected on email because I think it would be better to do that, just on your own for that.
Yes.
So I will connect both of you for that.
Yes, of course. Such question like, is a higher melanopic rating better? It is not automatically better. Melanopic rating is the strength of lighting to elicit biological effects. During daytime, it is supposed to be better, but during nighttime, of course, it is not better. So the right light at the right time, higher melanopic rating during day, but reduced melanopic rating during nighttime.
Okay, and then we have one question from Mike Wynn. A question on human biological clock functions. Would light's color temperature override the time domain factors? In other words, can we modulate light temperature to simulate day of night to human biological systems? I think what that means if somebody's like using graveyard shift.
Yes, of course. Shift work is a real critical problem. Everything what I have told you is ideal for daytime workers. Of course, for nighttime workers, it is strongly depending on the type of shift work they are doing. If they are really doing graveyard shift with rotating night shifts and all these problems, they have a disturbed sleep-wake cycle anyway. And usually I need, even with light, I need maybe one day to shift the biological clock by 3 hours. So if a shift schedule is changing by 8 hours, then I would need, even with optimized lighting, 3 days to bring somebody, to synchronize somebody again with a new shift schedule. So lighting and shift work is a very critical issue, and it can't easily be overcome. The first step should be to optimize shift work schedule in a way that shift work, for example, is more oriented on the individual chronotype. You can imagine a late chronotype, somebody who gets up very late during day and is used to be active until late in the evening, or even late at night. Somebody who doesn't go to bed before 1 or 2 o'clock a.m. For such a person, it is very easy to
continue, for example, working a night shift for 3 more hours and then go to bed in the morning. So a late chronotype can easily do night shift, and an early chronotype can easily do early morning shift. The problem is that we don't have an equal distribution of early and late chronotypes. We usually have more late chronotypes, so there might be a lack of people being able to do morning shift. That's one of the reasons why this has not been realized so far. But I know that some studies are ongoing to respect much more the individual chronotype of shift workers for optimizing shift work schedules. And then once the shift work schedule is optimized to the individual chronotype, then light can also be used to further support this.
Okay, well, thank you.
It's definitely a big problem which can't be solved by lighting alone, these shift work questions.
Well, thank you very much. So what I'm going to do is, again, a number of people have other questions. I'm going to email you and copy Dieter so you can email directly for you, because some of these questions are quite long and we're getting close to 10 minutes after. So I think we're going to call it a day. And I just want to say thank you very much, Dieter, for doing this from Germany, because we've had a number of other classes like this, and you brought up some issues that at least I have never been introduced to before. So thank you very much. And thank you all for attending. And so, so you have any final words you'd like to say, Dieter, before you sign off?
Okay, yes, I like to thank everybody for listening, and I like to say sorry for maybe not being able to talk as firm and as good as I'm not a native speaker. Sometimes I have to look for words, and sometimes it's even more difficult to talk on the phone, not seeing anybody, than giving a presentation in English to an audience which is present. So sorry for everything which was not so fully comfortable for you maybe, but I enjoyed it, and I hope you at least have also enjoyed it to a certain extent, and I will answer your questions as quickly as I can, and I hope that we can stay in contact on this topic.
Thank you very much, Dieter. John, do you want to say anything at the very end, or you just want to sign off?
I'm good. Thank you, everyone. Thank you, Dieter.
Goodbye. Oh, okay. And again, this is our last webinar until September. So we're basically taking the summer off. And we're going to be, we're revising the structure of the committee and how we're going to be doing things. John Wong, Rod Heller, and I have been in a lot of conversation regarding that, but we're basically taking the summer off. And one reason is because I have to write a book that I've been putting off, and the publisher is getting pissed at me. So I need to write this book this summer. So,
okay.
So thank you all very much, Dieter, and also the attendees. Thank you.
Yes, thank you, and good success in writing your book, and we will stay in touch, I think. Bye-bye.
Bye.
Thank you, Dieter. Bye-bye.